This is the AS3 2013 paper, practical paper 1, and it's question 3. So this question is ultimately asking us to work out the percentage yield of iodoethane, and it gives us it in broken up steps, but how I'm going to do it is just using the two equations and writing out the calculations underneath the questions, but I'll highlight when we get an answer of what they ask us for. So all the information is here, and also you've got your 4.85 here, which we'll use for our final percentage yield calculation. But we've also got some information on the previous page, so just be careful about that you always read to the previous page. So we'll go back to that now. So as I say, just be careful that there's that you've got all the information, even if it's on a previous page. So we've been given the method for preparing iodoethane. There's some description there. Here are the two important equations that we're going to be using in this calculation. And there's also some values here: 0.85 grams of red phosphorus, 5 grams of iodine, 5 centimeters cubed of ethanol. So there's important information here, and you're likely to be asked to use this boiling point range at some point as well, but we want to focus on these two equations for our percentage yield calculation. So you've been asked to work out the percentage yield of this, but obviously we've started with phosphorus and iodine, so we need to use this equation first. So part 1 asks us to calculate the number of moles of iodine used, and we need to use our first equation for that. So if we go back to the previous page, we can see that we used 5 grams of iodine. And I'm going to do this on a separate page underneath the first equation. But you don't really need the equation for this step, but I'm just going to do it all underneath the one equation. So we said that we have 5 grams of iodine, and we can work out our number of moles by using our equation, N equals mass over RFM. Now we have to remember that it's I2, so our RFM is going to be 2 times the relative atomic mass of iodine. So it's going to be 5 grams over 2 times 127, which is the relative atomic mass of iodine. And that gives us a value of 0.019685 moles. And that's the number of moles of iodine that we have used. Now you'll probably round that off to maybe 0.01969 or 0.0197. So that's your answer to part 1. Now the next part of the question asks us to calculate the number of moles of phosphorus iodide formed. Now usually we would have to work out which is the limiting reactant, because in the first part of the question we were told out how much phosphorus was used, but we can read in the question here that excess red phosphorus was used in the experiment. So that means for our first equation we can assume that iodine is our limiting reactant. So the number of moles of iodine that we worked out previously we can take as the limiting reactant and use that to work out how many moles of phosphorus iodide were formed. So again we'll go back to our equation. So we worked out that 0.019685 moles of iodine were used, and the reason we can use that is because we know that phosphorus was used in excess, so our iodine is always going to be the limiting reactant. So I can work out how many moles of phosphorus iodide were formed by bringing this up by my ratio. So my ratio, you can see, is 3 to 2. Now we're not usually we're used to having one of the ratios being 1. So what this means is divide by 3 and times by 2 to get the number of moles of phosphorus iodide. So you always divide by the number you had and times by the number you're going to. So if we divide 0.019685 by 3 and multiply by 2, we get that we have 0.01312 moles of phosphorus iodide formed. Part 3 asks us to work out the mass of ethanol used, And we can't just use the second equation to work out a ratio of this, because we're actually given the mass of ethanol used in the previous part of the question. So if you look here, you can see that we are told that we used 5 centimeters cubed of ethanol. So what the question is asking us here is the actual mass of ethanol that we used. Yes, it may be in excess, we may not end up using all of it, but that's how much the mass of ethanol that we added in the first place. So we've got that it's a volume of 5 centimeters cubed, and we're told in part 3 that the density of ethanol is 0.80 grams per centimeter cubed. So we can use our density equals mass over volume equation to work out the mass. So again, we'll do that under the relevant equation. So we're now going to move on to our second equation, which is this one. So I'll write that out on the next page. So I'll just write it underneath the ethanol part. So we have 5 centimeters cubed, and we know that our density is 0.8 grams per centimetre cubed. So rearranging our density equals mass over volume equation, we get that mass is equal to density times volume. So that's equal to our density, which is 0.8 grams per centimetre cubed, times by 5 centimetres cubed, which is our volume. And keeping our units in just double checks that we've got our right units, that we've got our volume in centimetres cubed rather than in decimeters cubed. Because you can see that these units will cancel each other out. Centimetres to the -3 will cancel out with centimetres to the 3. So 0.8 grams per centimetre cubed times 5 centimetres cubed is going to give us exactly 4 grams. So the mass of ethanol that we used is 4 grams. Now part 4, I'm not going to go back to the previous page, but part 4 asks us to work out the number of moles of ethanol used. And we can't just do a ratio. I know we have calculated the number of moles of phosphorus iodide that we produced, but we can't just use a ratio here. A, because it's a different question, but B, because we know exactly the mass of ethanol that we have used, and so we need to work from that in order to get our number of moles. So the question is really asking how many moles are there in 4 grams of ethanol. So again, I use my equation, N equals mass over RFM, which is equal to 4 over 46. 4 over 46 is equal to 0.086956 moles. Again, you'd probably want to round that off for the question. So, sorry, 4 grams was the answer to part 3, and this would be the answer to part 4. Now, at this stage, we have to work out which is our limiting reactant. Is it ethanol or is it phosphorus iodide? So part 5 asks us to work out the theoretical number of moles of our iodoethane, and in order to do that, to work out the theoretical number of moles, we need to decide which we're bringing over, the number of moles of ethanol or the number of moles of phosphorus iodide. And to do that, we need to work out our limiting reactant. So we know that we've used 0.086956 moles of ethanol, and from part 3, I think, we worked out that we have 0.01312 moles of phosphorus iodide that we have used. So we can use this number of moles, and also if we think, I'll write it up here, our first equation was 2p plus 3i2 goes to 2pi3. Now we worked out that we have 0.01312 moles of this. Now the reason that I use exactly that number of moles here is because, oh sorry, I forgot my 2 here. And the reason I can use that directly, 0.01312, rather than halving it, is because I don't use these balancing numbers between equations. I only use them within the one equation. So in this equation here, yes, 2 moles of phosphorus react with 3 moles of iodine to give me 2 moles of phosphorus iodide. But that doesn't mean then suddenly I have half the number of moles when I come to this equation. Okay, the balancing numbers are there just to balance one equation. They're not balanced between equations. And so when I say that in my first equation, this equation here, that I've produced 0.01312 moles, that's the number of moles that are available to go on and react with the ethanol. I haven't just suddenly halved the number of moles because there's now no longer a 2 in front of my phosphorus iodide. So when you're working between equations, so from equation number 1 here to equation number 2, you can take the number of moles of phosphorus iodide that we worked out to be the number of phosphorus iodide moles that go on and react with our ethanol. Because really in the first reaction you're talking about how many moles of phosphorus iodide you're producing, and that will then be the number of moles that goes on and reacts with ethanol. You don't get any less or any more. Okay, so I'll rub all of this out before we move on. So what I can see here is that I have 0.01312 moles available to react. However, in order to determine the limiting reactant, I need to divide through by my stoichiometric ratio or my balancing number. So you can see that in this equation, my stoichiometric ratio of ethanol is 3, and for phosphorus iodide it's just 1. So at this stage I'm dividing through by my stoichiometric ratio. So for ethanol I'm dividing by 3, which is going to equal 0.028985 moles. And for phosphorus iodide, there's no balancing number, so I'm just dividing by 1, which is obviously 0.01312 moles. And then at this stage, I take my number of moles that has the fewest number of moles. And you can see that that is still phosphorus iodide. So I use that to bring over to work out my theoretical number of moles of iodoethane. Now at this stage you need to be very careful when you've already divided through by your stoichiometric ratio. It's fine here because the ratio is 1 to 3 anyway. But say for example, and I'll just do this to show you, if we had brought over the number of moles of ethanol, well, you would be tempted to say that the ratio is 3, I'll just circle this, 3 to 3, which is the same as 1 to 1, but you have to remember that you've already divided by 3. So then the ratio, if you're using this number of moles, the ratio would have to be 1 to 3. Whereas if you were using this number of moles, the 0.086956 moles, then it would be 3 to 3. So just be careful of that. If you've already divided through by your balancing number, it'll be 1 to whatever you're going to always, because you've already divided through by the number. You've already essentially done the first step of the ratio. So I'll take all of that away before we move on. Okay, so we're taking this number of moles over to iodoethane, so that is a 1 to 3 ratio. And so I'll be a little bit squished here, but I can move all of this over. So 1 to 3 ratio means we times this this number of moles by 3, and that gets us 0.03937 moles. So that's the answer to part 5. The theoretical number of moles of iodoethane is going to be 0.03937 moles. Part 6 now asks us to work out the theoretical mass of iodoethane, and to do that we simply use mass equals N times RFM. Which is going to be 0.03937 times by the RFM, which is 156, which gives us a mass of 6.1417 grams. And that's the answer to part 6. So what that means is, theoretically, if nothing else goes wrong, if there's no side reactions, if absolutely all of our phosphorus iodide reacts, then we will get 6.1417 grams of iodoethane formed. But we know that in reality that doesn't happen due to loss of product when we're transferring between apparatus, and due to the presence of side reactions happening at the same time, so we don't always get all of our product formed. And so now we need to work out our percentage yield. So going back to the question, we are told that we produce 4.85 grams of iodoethane, and that is our actual yield. 4.85 grams is our actual yield, 6.1417 grams is our theoretical yield. So going back to our working out, we can work out that the percentage yield is the actual yield over the theoretical yield, times by 100%. So we're really working out the proportion of the actual yield over what we could have produced. So that's going to be our 4.85 grams, which was our actual yield, over 6.1417 grams, times by 100%, which equals 79.0%. And that is your final answer for part 7. Now you might have got slightly different values if you had rounded at various stages. I think Cia's answer was 79.1, depending on their rounding at different stages. But that's your general method. So it's important to look for your values in the different parts of the questions, look for your information. And remember that our mole ratios can only be used within one equation. If we're working between two equations, then we don't use our mole ratio. We take the number of moles produced to be the actual number of moles used in the second equation.